This conference will now be recorded.
Hello everyone. Today we will start basically a new chapter which is thermodynamics, because states of matter, that chapter is finished. But I would like to mention here one correction basically. So this problem we have done in the last class, which is based on states of matter. So here by mistake I have chosen the option which is saying that A for chlorine is greater than A for C2H6 and B for chlorine that is also greater than C2H6. So basically here correct option will be this one, where A for chlorine is greater than A value for C2H6, but it is reversed when it is the another van der Waals constant, which is B for chlorine. So B for chlorine, that should be lesser than C2H6. So when we will take decision that between two gases or three gases, in which case liquefaction will be easier, basically we just have to check A value and B value. So higher is the B value, liquefaction will be easier, and lower is the value of B, then also liquefaction will be easier. So remember, higher the value of A and lower the value of B, it will be easily liquefied, because when B is basically the total volume of all the gas particles. Fine. So when B value is very high, that means the size of the gas particles, suppose here B value is high, another case B is small, that means here particle is small. So here it is very high size, that is the particle size is very high, then liquefaction will be easy, it will be difficult. But when it is lower value of B, then it will be liquefaction will be easier. So this is the correct option, that is option B. A for chlorine is greater than A for C2H6, but B for chlorine is lesser than B for C2H6. So both are not same, A greater, B less. So now we are starting the new chapter. Here the topics that we are going to finish today is, first there will be introduction, then system and surroundings, types of system, properties of system, then different thermodynamic processes, reversible process, irreversible process, state function and path function, then if time permits, then internal energy, heat and work. So introduction is that is for thermodynamics, as we can say thermodynamics. So here this thermo, which means heat, thermos means heat, and dynamics you can understand it is from the word dynamic. Okay, so dynamics means it is flow, so it is all about heat flow. So this branch of chemistry, it is basically concerned with the flow of heat and the relation between heat and work. Fine. Now in our daily life, if we see some observations, there are many useful reactions such as flow of electrons through circuit to produce electric energy. So this is a day-to-day life. If it doesn't occur, then we cannot get light. That is household light I'm talking about. So why it occurs? It is because of the flow of electrons through the circuit, and it is producing the electrical energy. Then another example is metabolic reactions to produce the energy which is required for our body to perform different biological functions. So these are very practical examples of flow of, that is heat flow, or you can say the how heat and work is converting to each other, all these things. Fine. So here in the picture you can see how, because of chemical reaction, that is the petrol or diesel, we are applying to the car or any other vehicle, then what happens? It gets motion. So it is because of the conversion of one form of work to another form of work. So it is basically the chemical energy, it is now converted to this motion. Then as we take food, we get energy. Fine. Then from solar energy, there is photosynthesis, that, and from tree, as we take oxygen, so ultimately we get that oxygen. It does so many important biological roles in our body. And then from electrical, thermal. So these are some of the examples of energy transformations. So this thermodynamics, this chapter, it basically deals with heat and its relationship with energy in any one of its different forms. So energy, it may be different types of, it can have different types of form: mechanical energy, chemical energy, electrical energy. Fine. So in physics, mainly mechanical energy you will see. In chemistry, there is, we talk about chemical energy. In physical chemistry, there is electrochemistry chapter. Okay. So all these are basically different forms of energy. So these are some of the examples. There are many other examples of energy possible. But what is the relationship between these two? That is the all about thermodynamics. And one important thing about thermodynamics is that it is, here we deal with macroscopic observable properties. So when we talk about properties of any object, it is basically from two point of view you can consider. Macroscopic point of view, that is whatever in macroscopic scale we are observing. Another thing is microscopic point of view. So when it is microscopic, basically you are dealing with atomic, that is you are closely looking at the atoms or molecules, that is individual atoms or molecules, what type of properties are there, what roles they are playing. But when it is, we are talking about macroscopic observable properties, obviously we are not considering individual atoms or individual molecules. Fine. So for example, suppose we are trying to see pressure of any system, or temperature, or internal energy. So all these are basically examples of macroscopic observable properties of matter. So only macroscopic observed properties of matter, so these are some of the examples, are considered without assumptions of its atomic nature. So we are not dealing with its atomic, that is how it is affecting from the atomic level. That thing we are not doing that. It is all about macroscopic, not microscopic. Now one more important point, thermodynamics doesn't take into account the kinetic approach to the equilibrium state. So thermodynamics, then three things you can consider, I would like to mention here. So suppose I am talking about thermodynamics, I'm not writing full. Then we have another chapter, very important, chemical kinetics. Then we have thermodynamics, chemical kinetics, and equilibrium. So these are the three important chapters you will find in physical chemistry. So basically these three sections, it is very important for us to have clear idea. So chemical kinetics is the chapter where you will learn how fast the system or any reaction, not just say reaction in broader sense, if I say any system, that is a better term to use, how fast it will reach the equilibrium state. So suppose there is initial state and there is a final state. So how fast? So it is all about speed when you are talking about chemical kinetics. And when it is thermodynamics, it is basically whether it is possible, that is this conversion is possible or not. Suppose you are moving from state 1 to state 2, it may be chemical reaction, it may be any other changes also, that is physical change also. So it is all about that whether it is possible or not. So it is about the possibility. It has nothing to do with how fast we can reach the equilibrium state or not. So thermodynamics is all about possibility. Then chemical kinetics, that is all about how fast we can reach the equilibrium state. And equilibrium state is basically, you can understand that once you know from thermodynamics that yes, the process is possible, then from equilibrium, how much conversion is possible, okay, that we can understand. So simply if I say that A is starting material and B is product, so A is converted to B. So from thermodynamics you know that A can be converted to B. That possibility is present, because that possibility may not be present. That is, maybe this conversion is not possible. But suppose from thermodynamics you know this conversion is possible. So once you know this, then by applying the knowledge of equilibrium, we can understand how much conversion is possible. That is, how much B you can get starting from A. So that is all about equilibrium chapter, you will understand. And here also it has nothing to do with speed of the reaction. And what about chemical kinetics? Now once you know that it is possible from thermodynamics, from equilibrium, now you know that you can get, suppose 60% conversion is possible. that you can understand basically from equilibrium constant, that is we will deal with in another chapter. And chemical kinetics is how fast you can reach from A to B. Not necessarily that you will get B in higher amount or lower amount. That is not concerned in chemical kinetics. Chemical kinetics is all about how fast you can do so. Okay, so these are the three important chapters, and from these three individual chapters we can predict different things. So lastly, I'm saying thermodynamics is all about feasibility of the process. Chemical kinetics is how fast you can do so, and equilibrium is how much conversion is possible. Okay, so three different things. So thermodynamics, it is based on three simple laws that are not derived but are generalizations deduced from long experience with energy and of natural phenomena of the scientist. So in this chapter, basically there will be three laws. Though among these three laws, the first two laws are we deal with in detail. So these three simple laws, how they are derived, it is not that any direct experimental observation or like that. It is basically the generalizations. What type of generalizations? That is from different observable property things for a long period of time. Whatever we have observed for different systems, if we make some general conclusion, then you can say these are as if these simple three laws. Okay, so these are the generalization deduced from long experience. So it is not one day event. Fine. So maybe for many years, several years, it is long experience with energy and of natural phenomena of the scientist. So they have observed for a long period of time from different observations in different systems, and then finally they have made some generalized statement, and that is these laws of thermodynamics. Okay, so before actually starting these laws of thermodynamics, to understand all the processes, that is how we will be able to predict that this conversion is possible or not. Basically we have to know some important terms. Once you know these terms, because these terms will be used again and again throughout the chapter, so you should know all these terms individually. So that is why first we will see all these important terms, few terms, and they are used frequently in this whole chapter. So here you can see system and surroundings. So what is system and surroundings? What we understand when we will say, when we will use these terms, what we are actually trying to say. System is a quantity of matter, or you can say it is a part of universe. In bracket, what is mentioned, a collection of an extremely large number of atoms or molecules. So when we are talking about quantity of matter, obviously it is collection of many number of atoms and molecules, and you can also say it is a part of universe. Now this part of universe you have chosen for a specific purpose. You have chosen it for to make some observations. Okay, so chosen for observation purpose, and when you have chosen it, it is obviously separated by boundary from the rest of the universe. So here boundary is important. So for example, here you can see in beaker, suppose we have taken some solution. So beaker, with this solution, it is actually the system, and outside whatever you have, that is actually the surroundings. And when you combine these two, basically you are getting universe. Fine. So universe, in this way we can break it in two things, system and surroundings. So this is system, and outside it is surroundings. So if you consider the left hand side picture, system is within this yellow box, and then this area is surrounding. When you combine these two together, you can call it universe. Now remember here boundary is important. So in the first picture, this is the boundary, because if there is no boundary, how you will separate this system and surrounding? This must be separated condition. Okay, so here this beaker is basically this boundary. Now depending on boundary also, boundary may be different types. Sometimes it may be that boundary is such you can that is energy exchange with the surrounding is possible. but sometimes it may be so the boundary is made in such a way that even energy exchange is not possible. So different things possible depending on what type of boundary is present. Now this system, here example is any solution, or it may be water in a beaker. Another example is, suppose you have a balloon filled with air. So here the balloon, that is the skin of the balloon, that is actually the boundary. Then aqueous solution of glucose, etc. Fine. And what about surroundings? Obviously, except system, all the other parts of the universe, which is basically outside the boundary region. And obviously this is not a part of system. That will be called surroundings. Boundary is designed to allow us to control and keep track of movements of matter and energy in or out of the system. So boundary can be, that is, you can design it according to your whatever you want to do, according to your purpose of the experiment. It can be designed in such a way so that we can have some control and keep track of the movement of matter and energy. Matter is basically, that is a matter exchange means mass exchange, and energy exchange, whether these two types of exchange possible or not. Now depending on these types of boundary, what types of boundary present, we can have different types of system also. So now in this slide we have learned what is system, what is surroundings. Next we will see what are the different types of system, and that is based on what type of boundary you have. So depending on boundary, there may be movement, we can control the movement of matter and energy in or out of the system. So see, here we have taken a system, that is the beaker. It is open. So in this case, mass can be transferred, that is mass exchange with the surrounding is possible, and also heat exchange is possible. That means energy exchange is also possible. So it is called open system. So mass transfer, yes, it is possible. Heat transfer, yes, it is possible. So this is the example. You have taken any open beaker, that is, you have taken some open container, not necessarily beaker. So it is that system where mass, heat, or better we say mass, energy, both can be exchanged. Now the next system, now we have closed it. So once it is closed, but see, the beaker, it is made of glass, so it is not that you can through glass heat can be exchanged, so you cannot restrict that. But as you have closed it, no matter can be changed, that is, no matter exchange is possible with the surroundings. So here mass transfer restricted, only heat transfer, that is energy transfer, possible. So this is called closed system. And then there is isolated system where both are restricted. Mass transfer no, heat transfer no. Okay, so you cannot exchange anything. Now a better example for this is, suppose you have taken any liquid in thermoflux. So thermoflux, the wall is made in such a way that energy exchange is not possible. So when we keep any warm liquid, okay, so it remained warm for a long time, and that is because heat energy is not, it is restricted. Fine. So these three types of system, depending on matter and energy exchange possible or not. So open system, a system can exchange both energy and matter with the surroundings. Then closed system, a system can exchange only energy but not matter. And then isolated system, no exchange possible, whether it is matter or energy, nothing. Okay, so that is, it is completely isolated. So types of system. Next we have to know what are properties of system. Okay, so now we have proper idea about system. Then we also know what is the different types of system. Next thing that is important for us to know, what are the properties of system. Now these properties are basically experimentally measurable physical properties. And why we should know these properties? We should know these properties because if we know these properties, then only we will be able to define a system. So for example, volume, temperature. Remember in states of matter chapter, we have seen how we when we are changing the pressure, there is some effect on volume. So this pressure, volume, these are actually experimentally measurable, and these are physical properties. So suppose if you want to define a system, you should know properly what is its pressure, what is its temperature, its volume. So now we will have some idea about the system. So it is not enough to know whether it is open, isolated, or closed. That is obviously important, but after that, once you know this, you should also know these experimentally measurable physical properties. So some examples here you can see: number of moles, how many moles of the substance, any substance present. It may be more than one substance, obviously. Then what is the energy, temperature, pressure, density, etc., etc. Now some of these properties of a system, it may depend on its mass or size. So the system that you have taken, suppose in one beaker you have taken 500 ml of water, then another beaker you have taken 1 liter of water. So obviously mass is different, fine. So there will be some properties of system that are dependent on this mass or size. So what type of, suppose you have taken some metal. So in one case there is a particular size of metal, in another case the metal size is large. Okay, so mass or size in some cases matters. So if you change the mass or size, these properties are also changed. But it may not be so for all the properties. So now we can do some classification for these properties of system depending on whether it depends on mass or size or not. So one is called extensive properties. Another is called intensive properties. So extensive property and intensive property. So extensive property, this property, they depend on the mass or size of the system that you have taken, and it is called extensive. And intensive, obviously, here there is no dependence on the mass. So it is very easy to understand. See, suppose we are talking about temperature. Okay, now to know the temperature, you don't have to know what is the mass of this. So suppose in beaker you have taken some water, you have given some temperature, now it is hot. So now you are trying to measure the new temperature after giving this energy. So this, if you want to this new temperature, it is not that you have to know the total quantity of the water. That is not required. So temperature is example of intensive property. Then density also, it is basically mass per unit volume. So it is dependent on the, that is, once you know that this one unit volume mass, you don't have to know the, that is, total mass or size. Then surface tension. Surface tension, remember we have learned it in the last chapter, states of matter. Then one important difference you can see, when it is extensive we have example of volume, but when it is intensive it is molar volume. So if you want to know the volume of a system, obviously you have to know the mass or size. It is dependent on mass and size. But if it is molar volume means what? Volume of 1 mole. So you have already fixed the amount. It is 1 mole. It is Avogadro number of particles. So you have already fixed it. So that is why when you are talking about molar volume, basically you don't have to know the total mass or size. So that is why it is intensive. But if it is simply volume, then it will be extensive. Some more examples are also there, because based on this you can get question. So extensive properties, number of moles. So if you number of moles, if you do not know the total mass, how you will calculate the total moles? Then energy, then mass, obviously it is extensive. And here you can see some terms, though we have not learned it, but once you will, that is, this chapter will be finished and you will have proper idea about all these terms: entropy, internal energy, then G, heat capacity. Then also you will be able to see that all these are extensive property. Now look at intensive. Boiling point. So to check the boiling point, suppose you want to know the boiling point, fine. So you are just boiling water. So what amount of water you are boiling, that is not important. In both cases, whether you have taken small quantity of water or high quantity of water, you can measure boiling point. It doesn't, you don't need to know the matter of size. Then color, concentration, density, etc., etc. Now see, heat capacity and specific heat capacity. Basically, again I'm saying that we have not learned it yet, but specific means here amount is fixed. That is why once you have fixed the amount, then it is it falls under intensive property. It is no longer extensive property. Okay, and you can see here we have a molality also, because molality is the number of moles of solute present in 1 kg of solvent. So you have already fixed the amount in which you are measuring the number of moles. So from the definition of molality, it's number of moles of solute present in 1 kg of solvent. So here amount is already fixed, so that is why it is intensive. After properties of system, whether it is extensive or intensive, next is thermodynamic properties. Sorry, thermodynamic processes. So once we have proper idea about the system, that is, you know volume, temperature of the system, you also know whether it is closed, isolated or open, everything we know. Okay, next thing, suppose you want to bring some change in the system, but you can do this change in different way. You can change pressure, you can change volume, or you can change both. So different processes possible depending on which one you are doing. So basically you are doing some operation and there is a particular path you are following. Okay, so thermodynamic processes, it is basically the path or the operation by which you are bringing some change in the system. So that is why, as if now there is an initial state and there is a final state, and you are bringing some change. So this is the obviously the system, this is also the same system, but now you have done some changes, you have done some operation. So a process or thermodynamic process, it causes a change in the value of at least one of the state function. Now what is state function, path function, that also we will read today. Right now just see, you have to bring change at least one of the properties. Okay, so some examples of thermodynamic processes, here we have heating, cooling, expansion. So suppose you have some water you have taken in beaker, you are now heating it, so it will start evaporating, there will be boiling. Then you have taken water, you are cooling it, it will be converted to ice. So different things, operations possible. Compression, you have taken some amount of gas and now you are increasing pressure, you are doing compression. Okay, so these processes can be classified depending on how the processes we are doing. Okay, so depending on that we are having some classification. The first term here we have adiabatic process. Now here what is mentioned in the bracket, Q equal to 0. Now what is Q? Q is basically heat. So this Q, it means heat. It is denoted by small q. In some books you may also find it is written with capital Q, but mostly it is small q. Okay, so in that is by default you use Q letter to denote heat. Adiabatic process means you have to do the process in, you have to do the operation in the system in such a way so that there is no exchange of heat between the system and surrounding. So that is why it is written here Q is equal to 0. Then only you can call the process adiabatic process. Fine. Now how we can do it? You can do it if you thermally doing the insulation in the system. Then obviously heat will not be exchanged. Now when it is adiabatic process and you are, that is, work is done by the system, because there are two things possible. Either the system itself is doing work, or it may be that on the system there is some work done. So if the work is done by the system, that is one possibility, then what happens? Its temperature falls, internal energy also falls. So internal energy also in detail we will see separately. So it is basically the total energy that can be present in system in different form, not necessarily in any particular form. It may be thermal energy, it may be electrical energy, mechanical energy. That is summation of all the energy together, that is actually internal energy. But important point is when work is done by the system in adiabatic process, temperature falls, internal energy falls because it has done some work. But if work is done on the system, by the system, on the system. So when it is on the system, now temperature will increase, internal energy will also increase. Fine. So this point is important. Adiabatic process Q is equal to 0. Next process is isothermal process. Now for isothermal process, it is mentioned in the bracket del T equal to 0. Now if you are thinking that why not in the previous case we have written del Q, but here it is written del T. That also gradually we will understand once we know what is path function, what is state function. So probably in today's class we will be able to finish that also. So remember, temperature, that is absolute value of temp of any system. Suppose initial temperature 100 degree, final temperature 200 degree. So these absolute values are here basically not important. So when you are doing this operation, what is the difference in change that actually matters? Okay, so here 100 to 200, that is the difference. That is we are doing the operation. So difference is 100. 200 minus 100 is 100. So important point is whether there is any change in temperature. So suppose you are doing the process initial state, final state. So initial state 100 degrees centigrade and final state also there is no change in the temperature. So it means it is del T, TA final minus TI, that is del T. Difference. Del means difference. So this is basically this difference. If it is 0, that means there is no change in temperature. Then you will call this process isothermal. Okay. So remember, it has nothing to do with individual temperature of initial state or final state. You just have to know whether there is any difference or not. Difference 0 means it is isothermal. So in this case, the system exchange heat with its surroundings. Now in this case, obviously Q is not necessarily it is 0 because both 0 together it is not possible. You cannot say that the process is isothermal as well as adaptive. No, that is not possible. Fine. So system now can exchange heat with its surroundings. As a result, don't think that temperature will change. It is true that exchange of heat is occurring, but temperature of the system will not change. Now under this case, expansion may occur. Suppose there is some gas you have taken in a container and the wall is flexible. So expansion can occur when there is absorption of heat. And compression can occur, that is the opposite process. Volume of the gas will decrease with evolution of heat. That means what? Heat is exchanging with surroundings. That is possible. Now isothermal process, it can made reversible also. Now reversible, irreversible, that also we have not finished that. What is reversible or irreversible? Okay. So when we'll read it, it will be clear to you. Fine. Thermostats are devices that can maintain a constant temperature value if you want to do the operation in the system isothermally. So if we want to do this process with maintaining the condition that del T should be 0, we can take the help of thermostat because it is such a device which will help us to maintain constant temperature. Okay. Then isochoric process. Now just like del T 0, it is now del V 0. So no change in volume. In this process, the volume of the system remains constant during its change from initial to final state. So suppose initial state there is some gas and its volume is 1 liter. Final state also same volume must be present. Then only it is isochoric. Example, combustion of fuel in Bohm calorimeter is an example of isochoric process. So Bohm calorimeter, it is such a device where when we do combustion of fuel, that is suppose any hydrocarbon you have taken and then you are burning it in oxygen, there will be production of carbon dioxide and water. There will be a tendency to change in volume, but this device is such, it will help us to keep volume same. Okay. Isobaric process, del V equal to 0. So pressure will remain constant. You have initial state, you have final state. Initially there is suppose 2 atmosphere pressure and final pressure is also 2 atmosphere. So PF minus PI del P is 0. In this process, pressure of the system remain constant. Example, boiling of water to steam or freezing of water to ice. So you can see this is basically phase change. Water when it is in liquid form and now you are changing it to gaseous form, that is conversion to steam when it has reached its boiling point. Remember when we give definition of boiling point or melting point or freezing point, it is at particular temperature, particular pressure, because during this phase change there is no change in pressure. Okay. Cyclic process. Now cyclic process, it is broader thing because here different things are 0. Now these two we have not learned yet, but once you know this, then you will see these two are also basically another kind of state function, but these three we know. So in cyclic process what happens, suppose you have started at point A, you have another point B. Okay, so when you are moving from A to B, this is one state, initial state, this is final state. But suppose you have started your journey from A, you are doing different operations, whatever path you are followed, but still your ending point is also A, it is not B. So that is called cyclic process. So you have started at the point, you have reached the same point. So obviously initially whatever is the pressure, whatever is the volume, whatever is the temperature, you are reaching the same state. So obviously del P, del V, del T, all these things will be 0. Del U, del H, these are just like these three. We will also know it. But just based on these three, you can understand. This is cyclic process. You have reached the same state. You have not changed the state. Okay. Whatever path you follow. Suppose you are following another path or any other path, different path, but ultimate point is you have reached the same point. That is what is cyclic process. So after completing a series of changes, not necessary in each path the series of changes should be same. Suppose this is path 1, this is path 2, this is path 3, whatever path you have covered, but you have reached the same distance, same point from where you have started. So that is what is cycle. So when you have this type of operation, we can say that the cycle is completed and the process is known as cyclic process. Fine. So in this picture, we have taken 4 points, A, B, C and D. Now we are saying that when we are moving from A to B, suppose it is 1. So in this case, initially it is P1, B1, T1. Now when you have reached B point B, it is basically there is change in temperature. Now it is T3 and there is change in pressure also, but volume is not changed. That means this axis, it is basically volume, because see here also if you draw a line on the x-axis, it is basically volume, same volume, whether you are at this point or at a point, in both cases volume is same. Okay, so that is, it is isochoric. And y-axis there is pressure. How we are understanding this? Because when you have moved from B to C, see P3, P3. So in both cases pressure is same. So that is, it is mentioned isobaric. Fine. Then we have moved from C to D. Now in this case, all these three change. So that also it is clear, because when you have moved from C to D, at point C, you have this pressure and you have this volume. When you have reached D, now the pressure is here. If you simply extend this point, and this is the pressure. So P, V both changed, right? So everything changed, and this process is basically adiabatic. Though from this plot it is not clear how it is adiabatic, but just we are trying to summarize it in a single plot. Fine. Then you are moving from D to A. So you have reached your initial state by covering different paths. And in this case, now temperature is same, though as it is PV curve, we will not be able to understand that. But see, P and V both change because the point D, this is the pressure and this is the volume. When it is A, this is the pressure, this is the volume. So obviously P and V changed, but temperature is fixed. So that is why we are calling it isothermal. So A to B isochoric, volume fixed, B to C, pressure fixed, C to D, no heat change, D to A, no temperature change. Different operations you have done, but ultimately you have reached A. So if it is so, it will be a cyclic process. That is a net change in P, V and T, everything 0. So now we are summarizing it again in this table. Sometimes instead of writing del, suppose I am writing del T, you will also see it is mentioned as dt. So dt is basically, it is also change in temperature, but it is when the change is very small, we use small t. Okay. So adiabatic, here we will not use any del or d sign because it is not state function. We will also see what is state function and path function. But for path function, there is no, you cannot use this type of del sign or d sign. So isothermal, no change in T, isobaric, no change in pressure, isochoric, no change in V. And when it is cyclic, everything 0. E is basically internal energy. Sometimes in some books, another letter is followed, which is U. So whether it is U or E, both are actually meaning internal energy. Fine. So another representation in PV curve, isochoric, see, this is parallel to y-axis and it has to be because there is no change in pressure. Then, sorry, there is no change in volume. So here also, if you draw a line on x-axis, this is the volume, here also same volume. Then if it is isobaric, now it will be parallel to volume, that is parallel to x-axis. And for adiabatic and isothermal, these type of lines you will get. Fine. Now, why in case of adiabatic and isothermal, these type of difference we are seeing, gradually we will be able to understand them, not right now. Okay. So reversible process and irreversible process. So when we are saying that it is a reversible process, now if from initial state to final state, when you are moving, there is actually series of changes carried out on the system. Then it is done in such a way, suppose this is one, this is actually very small changes we are doing. Okay, series of changes. So this is one change, then another. So in this way, suppose we are doing some series of changes from initial to final state, and we are doing it in such a way that it may be possibly reversed in exact manner. So the series that you are following here, you can also, when you are moving from F to I, final to initial, reverse path, then it will be following the exact initial and final state. Now this is possible if you are doing the change very slowly in smaller steps. So see here I have mentioned some smaller steps. So you are not doing it suddenly or abruptly. You are doing it very slowly. Small steps you are following during its change from initial to final. Because if you are doing it abruptly, suppose initially there is one P value, Pi, final is PF. So if you are doing it abruptly, what will happen? The change from Pi to PF, it is sudden. But if you are doing it small change, what will happen? In each change, that is in each small change, the pressure change, it will be almost nil. So very small example if I see, suppose initially there is pressure 1 atm and final pressure is 2 atm. But if you are not doing it abruptly, if you are doing the change very small, so the difference you are doing it, that is the first change that you have done. Suppose it is you are increasing the pressure or decreasing. Suppose you are increasing. Suppose it is 1.000 something. you have increased 1.0001. So it is almost equal to 1. So that is why I'm saying you are breaking the steps in some smaller steps. You are not doing it abruptly. So why you are doing so? Because our motto is to maintain almost same change in pressure. Here I have taken pressure. It may be any other property also. And just taken this example. So suppose from 1 atm now you are changing to 1.001. Then from 1.001 it is 1.002. So in this way, very slowly you are changing the pressure so that in each step, the initial and final for each step, it is almost same. So as if the del value is almost 0. So you have to do this in such a way. If you can do so, then you can call it reversible. So by doing so, each of its intermediate state, it will be in equilibrium with its surroundings. And under such conditions, the initial and final states of the system become irreversible completely. So in this small change, suppose this is 0.1 and this is that is state 1, this is state. So first you are moving from 1 to 2, then you are moving from 2 to 3. These are very small. Then you are moving from 3 to 4. So these small changes you are doing in such a way that in every change there will be some equilibrium. So you are moving from 1 to 2, but following the same path you can also move from 2 to 1, then 3 to 4, 4 to 3. Okay, so in each step reversibility must be maintained. Then only that is equilibrium must be maintained. Then only we can call it reversible. So when ice melts, a certain amount of heat is absorbed. So you are providing heat, ice is melting. Now it is converted to liquid water. Now the water that you have obtained from ice, you can convert it back to ice. Provided now you are extracting the same amount of heat from liquid water. But by moving the same path, you can also go back to the initial state, which is ice. Fine. So it is also, though we are saying so, but it is also true that when you are providing heat and ice is converted to water, now the reverse process, it is basically not spontaneous. Okay, so you have to forcefully extract the heat, then only it is possible. So that is, we will see most of the reversible processes are basically not unidirectional or not spontaneous. So most of the change that if you observe in nature, you will see most of the changes are spontaneous change and most of them are unidirectional. So reversible process as if it is ideal situation. Fine. So reversibility, it is actually, you can associate the term with equilibrium. Though I am not saying that because equilibrium, it is it may be two types. It may be dynamic equilibrium or it may be static equilibrium. Now static equilibrium mostly in chemistry we do not use. So when it is dynamic equilibrium, that is the movement from initial state A to final state B and the movement in the reverse direction, both are going on simultaneously and it is not stopping, it is going on. So that is why we call it dynamic equilibrium. Fine. So that is you can associate it with reversible processes. Fine. So for a reversible chemical reaction, an equilibrium state is attained when the rate at which a chemical reaction, now suppose you have taken a system where some chemical reaction is going on, because it is not necessary always it has to be chemical, it may be physical change also. Just see, ice is converted to water or water to ice, it is basically physical change. The chemical composition of water is not changed, it is still H2O, 2 hydrogen 1 water. But suppose you are doing some chemical reaction and in the chemical reaction reactant R is converted to product P. So here the rate at which the chemical reaction is proceeding in forward direction from R to P equals the rate at which the reverse reaction is also proceeding. So when this reverse reaction rate and the forward reaction rate both are actually going on simultaneously, equal rate, then you can say that it is reversible and it has reached this equilibrium state, and this type of sign we use for a reversible process. Now once you understood reversible, so obviously when it is irreversible, which is basically most of the common natural observation that we see in nature, most of them are basically irreversible. So you cannot retract to initial state easily. So if you want to do so, you have to make some permanent change in the surrounding. It is not natural. So suppose take the example of biological aging. It is irreversible process. Water flowing down a hill on its own accord. Now if you want the movement of water from down to up, it is obviously not natural. You have to make some effort for that. Okay, so that is it is written. It cannot be retracted to initial state without making permanent change. So you can do so, but you have to give some effort, and there will be some permanent change in the surrounding. So without, that is keeping the surrounding intact, you cannot do so. So that is we say in definition of irreversible process, and most of them are spontaneous. But if you consider reversible, that is more ideal situation, and that is non-spontaneous. So reversible and irreversible, if we compare, it is basically ideal process. And see, as we have mentioned the conditions, you have to do it in several small infinitesimal steps, and it will take a long time. So infinite time it will take. If you actually want to do that is ideal reversible process, if you want to follow, obviously it will take very long time, because at each small step you have to maintain the equilibrium at every intermediate step. So it is ideal case, and irreversible, it is spontaneous, and it is not taking infinite, it is taking finite time. Now in reversible, basically you will see work obtained maximum compared to irreversible, because in reversible you are taking utmost care in every stage so that there is no loss of energy. But irreversible, you are doing the change abruptly. It is unidirectional, so there may be some loss of energy. Okay, so that is why you will not be able to fully convert, though in reversible also it is not possible to fully convert the energy to one state to another state, but maximum work you can achieve compared to irreversible, because of this loss of energy tendency. In irreversible, work obtained is not maximum. As it is ideal, it is basically imaginary process, cannot particularly realized in actual practice. So you may reach that is, if we are saying something is reversible, basically it is close to irreversible, but exact ideal situation, if you consider, it is basically imaginary, but it is comparatively natural, because it occurs in a direction under given set of conditions. So here we use unidirectional arrow, and here this type of sign is used. But in general, you will see that sometimes we do not use this type of arrow, double both side, because if you do not know properly whether there is actually reversibility present or not, you directly cannot use this. And once you know this, then you can. So unless you know this, you can simply write this type of arrow. Fine. Then state function and path function. Remember, when we write q, we have never written del q, but when we have written change in t0, we can write in this way. So there is no such thing as q2 in one state 2 or q1 in state 1. You are taking del q. No, this is absolutely wrong. It is not possible. This is possible only for state function. But what is state function? So state function is a thermodynamic property which has a specific value for a given state and does not depend on the path or manner by which you are doing the change. So there will be some initial state 1, final state 2. So from 1 to 2, you can move in different path, but which path you are following is not important. Whatever path you are following, you will always reach the same state. So from state 1, suppose you are moving in straight line, you have reached state 2. In the second case, you are not following a straight line, you are moving in a different way. But whatever it is, suppose your temperature is T1, your temperature is T2. In the second case also, as state is fixed, here also it is T1 and T2. So in both cases, del T will remain same. Fine. So what path you are following, that doesn't matter. But when it is, okay, another example also see. PV curve we have taken. So you are moving from one point to point number 2. So at point 1, this is the corresponding pressure, this is the corresponding volume. At point 2, this is the corresponding pressure, this is the corresponding volume. So in both cases there is some change. Now you may follow path A or you may follow path B, but it doesn't matter because you can also follow suppose another extra path I'm drawing, or you are following any path. Suppose this is C path, this is D path, whatever you follow. Point is you are reaching to where the value of P is these two and this is the volume of P. But when you are at state 1, you are having this pressure and this volume. So in this way, you can understand this is state function. It is also true for pressure, volume. Then we have enthalpy, though we have not introduced this term yet. But path function is not so. It depends on the path which you are following. So if you are following path A, there will be one type of Q, that is heat change. If you are following B, then there will be another. So path function is that thermodynamic property whose values depend on the path that you are choosing when you are moving from initial to final state. And work and heat, these two are such a thing which are dependent on path. So that is why you will see we never write del Q. Absolutely wrong. We never write del W, change in work. That we do not write. So work and heat, these two will have different values if you are doing it reversibly, irreversibly. So remember we have said reversible process, you can get maximum work. But if you are following some irreversible path, that means now you are not following same path. So path 1 irreversible, path 2 irreversible. So work obtained different. So that is why work is path function. It matters on which path you are choosing. So that is why it matters whether you are doing it reversible or irreversible. But if it is suppose change in P, it doesn't matter whether it is reversible or irreversible. Fine. Okay, so we are at the end of the time. We have just finished up to state and path function. Next day we'll see what is internal energy, what is heat and work in detail. Okay, so we are ending it here. Thank you for listening.